Road to Olympiad.
Welcome to RTO. Consider the following problem. Let P, Q, and R be positive real numbers, not all equal, such that sum 2 of the equations, px squared plus 2qx plus r is equal to 0, qx squared plus 2rx plus p is equal to 0, and rx squared plus 2px plus q is equal to 0, have a common root, say alpha. Prove that alpha is real and negative. Also, prove that the remaining third equations have non-real roots. Since two of them have common roots, it will be pretty straightforward that we can substitute alpha into two of the equations. But the next problem is, how are we going to deal with the two equations to show that alpha is real and negative? Pause the video if you'd like to give this problem a try, and when you are ready, keep watching to learn how to solve it. To solve this problem, without loss of generality, we can start by assuming that the first two equations are having the same roots, alpha. Substituting alpha into the equations, we have p alpha squared plus 2q alpha plus r is equal to 0, and q alpha squared plus 2r alpha plus p is equal to 0. Multiplying q into the first equations, we have this. And multiplying p into the second equation, we have this one. Doing so, we can subtract the two equations to get 2 times q squared minus pr times alpha plus qr minus p squared is equal to 0. Now, we claim that q squared minus pr cannot be 0, and thus we can solve the equations for alpha. To do so, we see that if q squared minus pr is equal to 0, the equation just now will give us qr squared minus p squared is equal to 0. This is simply equal to p squared minus qr is equal to 0. Multiplying q, substituting q squared is equal to pr from the fact that q squared minus pr is equal to 0, we have p squared q minus pr squared is equal to 0. We can divide by p here since p is given to be positive. And so we have pq minus r squared is equal to 0, or r squared minus pq is equal to 0. Adding the three equations involving p squared, q squared, and r squared, we have p squared plus q squared plus r squared minus pq minus qr minus pr is equal to 0. Which we can multiply the entire equation by 2 and rewrite it this way. So we can factorize each part of them into this one. This gives us the sum of 3 squared to be equal to 0, and this can only happen when each of the term in the square is equal to 0. And thus, we have p, q, and r must be all equal. This is a contradiction, as p, q, and r are given to be not all equal. Therefore, q squared minus pr must be non-zero. With this, we can solve for the equations and obtain alpha to be equal to p squared minus qr over 2 times q squared minus pr, which is clearly a real number. Now, we can let beta to be the second root of px squared plus 2qx plus r is equal to 0. By the Vitas theorem, we have the product of root to be r over p, which is a positive number since p and r are positive. This implies that alpha and beta must be of the same parity. Also, we have the sum of root is equal to negative 2q over p. Since p and q are also positive, we have the sum of root is negative. Here, we have sum of two numbers of the same parities is negative. This implies that both the numbers must be negative, which conclude our first proof for alpha is real and negative. The second part is rather easy. To show that the third equation have no real roots, we can check for the discriminants, which is equal to 2p the whole thing square minus 4r cubed. This can be expanded and factorized into 4 times p squared minus qr. Notice that since alpha is real, the first equations must be having real roots. In particular, two distinct real roots. and thus its discriminant, which is 4 times q squared minus pr, must be positive. Combining the fact that alpha is negative, we must have p squared minus qr is negative, which conclude our second proof. And this marks the end of our solutions. Post in the comment below if you have any thoughts on the video, and if you haven't subscribed yet, consider subscribing. This will really help us out. Anyway, see you in the next video. Thank you.